So this is one where these are easy because the vectors are what? What makes this problem easy? The two vectors that we're adding up are what? Well, straight. But what do you mean? I think you mean something different. Horizontal and vertical, right. So when the vectors are completely horizontal and completely vertical, they're really easy to add up, aren't they? So in this case, we've got one that's heading due east, and we know east is this way, right? North is up. Okay, so that's like in the positive x direction. So we've got a vector, oops. So we've got one vector kind of going out in this direction, right? And then we've got another vector that's going due north, right? So like this. And if we want to write some numbers on there, this one has a magnitude of 3.1, and the units are going to be the same, right? Meters per second. And this guy down here has a magnitude of 16. And what we're trying to do is just find the resultant, right? So the vector that goes from down there up to there, and that's R. And then we want that angle theta. Okay. Make sense? How are we going to do that? Pythagorean theorem, sure. So that's just a calculator issue. So let me pull up my calculator. So this is one where I would like to encourage you to do the entire calculation at once on your calculator. It ends up being easier. So tell me if this does or doesn't make sense. So we're going to go square root of 16 squared plus 3.1 squared. Does that make sense? Okay. And 16.29. It looks like we've only got how many significant figures? Two. So what's that going to be? 16. Good. Okay. What about finding the angle? Okay, I got to do arctangent, don't I? Because now, and this is where I want to make sure the trig stuff is going to be much trickier for some people. So here's our right triangle. Think of what a SOHCAHTOA triangle looks like. A SOHCAHTOA triangle, that's theta. We have to label the legs and the hypotenuse, right? So here's the hypotenuse. Is that going to be, Brady, is that going to be opposite or adjacent? If that's our angle. What do you think? Opposite, good. So that's opposite, which leaves right there, right? Okay, so then what's the two legs that I know are those two, right? Those are the ones I calculated, if that makes sense. So then if I want to find theta, I've got to use tangent, right? So the equation we have is tangent of theta equals the ratio of opposite over adjacent. Let me just write SOHCAHTOA. That's what that tells me. Tangent of the angle is the ratio of opposite leg over adjacent leg. Okay? So we can do that. Well, that's equal to then 3 over 16. We get that? Okay. So how do I get the theta there? You know, if we want to undo the tangent, how do we do that? Ezra? Oh, say it again.
If 3.1 would cover that.
Oh, yeah, I am. You're right. 3.1. There we go. So how am I going to undo the tangent? So I've got to solve for theta. Okay, the inverse tangent, right? We're going to take the inverse tangent of both sides. When I take the inverse tangent of the tangent, they cancel. And I just get the theta. And then on this side, I get the inverse tangent of that number, right? Okay, and that's a calculator question. So we go, make sure we're in degrees. We go second tangent of 3.1 divided by 16. And so what's our angle? 11. to 2 degrees, or to 2 significant figures, right? Oops. Okay? All right. Give me a 1 to 5. 5 meaning, got it, 100%, got that. 1 meaning, I have no idea. How are we doing? Okay, we're great. Okay. Never mind, wow. That's good. Okay, so now let's move on, and let's look at a little different problem. Something like this. This is a hard one. Picked a really hard one here. That's okay. We can make short work of this. Let's look at this 2 ways. Now I'm going to look at this first. Let's just look at what the vectors might look like if we drew the vectors in. But we're not going to do it this way. Right? I just want you to be clear what we're actually doing with this. So So, first one is going to be 8.2 meters per second at 36 degrees north of east. Deshaun, what does that mean? Explain to me. When they say north of east, it's good. So I'm going to start, good. I start at east, and then I'm just going to rotate up, right? Until I get to 36 degrees. So the first one looks like this. Maybe out like that, how about, huh? And that one's 8.02. Okay. Next one. Next one flows due northeast. What does that mean? 45, yes, it's going to be at a 45-degree angle. And it's got a magnitude of 5.01. So now, how would I draw that tip to tail on there? The vector by itself would just be at a 45-degree angle. But the thing about vectors is, and we haven't really talked a ton about this vector stuff yet, but we're getting into it now, more and more. If I take this vector, 5.01, at 45 degrees, if I want to combine it with this one, I've got to add them tip to tail, right? So I've got to take this vector and drag it over here. So it's tip to tail. You can do that with vectors, by the way. Vectors, you can slide them around wherever you want to. When you need to add them up, they must be slid so that they're tip to tail, right? Maybe something like that. And then I'd almost have to maybe do that. So that's my 45-degree angle. Does that make sense? And I guess I forgot to put this other angle. This is 36. And then the last one is, now this is tricky. It's 6.41 meters per second at 40 degrees east of north. What does that mean? Okay, good. So now we're starting at east. We're rotating down, right? Starting at north, I'm sorry. Starting at north and we're rotating to the east, right? So if I drew that one by itself, it would look kind of like this. It's gonna be 6.41, and there's the angle, right? We see that? 40.0 degrees, I guess. I did put the point zeros, but they're there. Right? So if I take this one and slide it over, this looks messy, doesn't it? Okay, agreed? And so the resultant then is going to be the vector that starts down here and ends right there. Agreed? Make sense? That's a pretty bad way to do it, though. Add all those vectors tip to tail, that's a lot of geometry. We don't want to do it that way. What are we going to do instead? Keep them separately. Yeah. We're going to take each vector by itself, break it up into horizontal and vertical components, and then just add those horizontal and vertical components up. The sum of all the horizontal components is going to give me the horizontal component of my result. That's pretty bad, Arrow. Is the horizontal component of my resultant vector, and the sum of all the vertical pieces of the vectors, when I add them up, becomes the vertical component. We don't do that on a graph, we do that on a table, right? So let's take this, and instead of doing it this way, let's just build a table. And when we're all done with the table, we can build just this orange right triangle by itself. Does that make sense what our strategy is? Okay? So, oh, that's not good. All right, so one more time. So we got this guy. Oh, gee. Degrees. Okay, we got that one we got to add up. We've got this one. And we've got this the last one's tricky, right? The last one goes like 40 degrees. The magnitude was 6.41, right? Question?
Like when it asks for the answer, how would it, like I don't understand how the scooter part.
Oh, yeah, yeah.
Goes into that.
So if the passenger, is it asking, on this one, it doesn't, okay, the answer just wants like the boat or something, doesn't it?
Yeah, relative.
Okay, that was a mistake. It's supposed to be the scooter. Yeah.
So
I
the
need to check
answer
that out.
is for the scooter.
I figured that out the hard way.
Yeah, it is for the scooter. I wrote the question wrong, I guess. So it is for the scooter, yeah, relative to the shore. You're right, so that was, sorry.
Okay.
So I'll change the wording on it, but that's, if you wanna get the answer, that's what you gotta do, yeah. Okay, so now we need to break all these up into components, right? So let's look at what these components are gonna be. So on this one, over here, my components are gonna look like that, horizontal and vertical, right? Here we're gonna get horizontal and vertical, but on this one, this is the angle, isn't it? So this is my vertical, and that's my horizontal. Now I could just as easily, if you want to, if this angle is 40, Olivia, what's this angle right here gonna be, do you think? If that one's 40, what's that one gonna be? If that's a right angle. 50, good, because you know they gotta add, what do you call that when angles add to 90, remember?
Complementary.
Complementary, yeah, complementary. So you could also, if you wanted to, this is optional, but you could do this, if you'd prefer, you could draw that same vector and use this angle. Does that make sense? So these would be the components. Either way, it doesn't matter, okay? Okay, so now let's turn all this into a table. All right, so on our table, we just want our table to have vector, the x component, and the y component. All right, so the first one, we'll just call this vector 1. Doesn't matter, right? So the x component is right there, isn't it? It's the horizontal one. What is this one for anyway? This is for the, is that for the boat?
The ship, yeah.
The ship, okay, so let's call this one B for boat. So that's B sub x and B sub y.
Okay.
right?
Mm-hmm.
So then what's b sub x gonna be? Now, don't say anything out loud. I want everyone to take a look at this. I want to make sure we understand why this is the case. B sub x. If we draw a SOHCAHTOA triangle, so there's the right angle and there's theta. We already said, right, that this is the opposite leg, adjacent leg, and hypotenuse. So if I'm trying to find out, let's say this one over here, for example, is the one that we're trying to find, hypothetically, right? If we want to find this guy, let's just call it x. We know that we're going to have to use which SOHCAHTOA relationship if we also know the hypotenuse? Everybody agree it's sine, right? Because when we spell out SOHCAHTOA, the sine is the one that uses the O and the H, right? Okay, so then we know that's the one that we would want for the y component up here. For the x component, what would it be? If we were trying to find this side, it'd be cosine, okay? So you don't have to do this every time. I'm gonna review this one more time, but then after that, don't do it anymore. You can take a shortcut on this step. So we know then that in this triangle up here, the sine of 36, or cosine, I'm sorry, cosine of 36 equals what ratio? From this triangle?
B sub x over.
Yeah, does that make sense? So it equals b sub x, which is what we're trying to find, over the hypotenuse, which is 8.02, right? To get the b sub x by itself to solve for it, how do you undo dividing by 8.02? Multiply. Okay, so then we'd end up with b sub x equals 8.02 times cosine 36. Okay, but I would say you don't even have to think about it in such a complicated way. Really, all you have to do is you just have to remember, I always know that when I'm finding the component of any vector, the horizontal or vertical component, I'm always going to multiply the magnitude by either sine or cosine, every time, right? So all you have to do is just, you start off by writing, well, I know the magnitude is 8.02. I just have to ask myself, is it a ka or a so? It's a ka, isn't it? Right? Because I'm using adjacent, for that angle, I'm using adjacent and hypotenuse. So 8.02 cosine 36 degrees, right? Okay, so what about the sine? Same game we're going to play. Okay, so for the sine then, that's going to be this component, b sub y. Oh, I should have given that away. For b sub y, how am I going to write that one out? What's going to be the first start of it? Deshaun, what's going to be the first part of that? B sub y equals what? The y component.
8.02.
Good, got to multiply the magnitude times sine, because this is a so, right? That's opposite, and if I'm trying to find that guy, it's opposite and hypotenuse. Okay, good. So let's look at the red vector. That was the current, right? Wasn't it? Okay. So we'll call this C, and then that's going to be C sub x and C sub y. Okay, so let's see. Brady, what's going to be, if I want to find C sub x, then what's that going to be? I know the magnitude's 5, the whole thing is 5.01. So what do you think? Perfect. 5.01 times the cosine of 45. Okay, and Morgan, what's going to be C sub y?
It's gonna be 5.01.
Sine, good. Sine 45, good. And then last one. This was the scooter, right? So we got scooter, and this is, oh, hang on here now. Look. Where's, on this one, where is S sub x?
On the left.
Up there, isn't it, right? Because we broke this vector up into these two components. Everybody see that? Because our angle was 40 on this one. unless you chose to use the 50-degree angle. Either way is fine. Right? Agreed? So with this one then, if this is C sub x, and that is C sub y, this one's a little tricky, right? We did? Oh, sorry, S. Thanks. Sometimes my brain and my mouth don't communicate very well, I think. So S sub x and S sub y.
This is a dumb question, sorry, but so 40 degrees, wouldn't it be like opposite over adjacent that way? So wouldn't it be y? I'm just a little.
Well, okay, but think about the coordinate axes. The coordinate axes always look like y
Yeah.
and x, don't they?
Oh,
See
so
what I'm
you're
saying?
going on that.
Yeah,
Oh,
yeah. When
okay.
we say, right, that's a good question.
Okay.
You gotta clarify that. When we talk about like, a vector, the x component or the y component, we're always talking about the x component is always the horizontal component, because that's the one that's parallel to the x-axis, right? And the y component is always the vertical component, okay?
Thank you.
Okay, so then on this one, now this is a little tougher. On this one, Sydney, what's gonna be then, if that's the way we're drawing our triangle, what's S sub x gonna be?
Okay, so S of x is gonna be 6.41, and then it's gonna be sine.
Yeah, sine. Everybody see that? Okay, because if we're looking for S sub x, if that's our angle, isn't that a SO situation? Opposite and hypotenuse? Okay, so, and then S sub y, Nicole, what's S sub y gonna be then? Good, cosine 40 degrees. And all we've got to do now is just add those up, right? We're just going to go down here to the bottom of the table, and to find the resultant, we just need to know what's R sub x. Oops, that's not a vector. R sub x equals what? R sub y equals what? R sub x is just the sum of all those numbers, right? R sub y is just the sum of all those numbers, okay? Now watch how easily we can do this in our calculators. This is good. I think it's good to learn how to use these calculators in a really efficient way. So right there, we'll do that. All right, so if I want to add up all of these, 8.02 cosine 36 plus 5.01, you see what I'm adding? Cosine 45. I'm just adding up all of the x components in the column on our table, plus 6.41 sine, right? Sine 40. And I get an answer, okay? Am I going to write that answer down to use it? No, I'm going to leave it on my calculator. On the calculator, it actually takes it out to like 20 decimal places, right? It's a very accurate answer. So we'll leave that there. Now I got to go do all these ones. Is there a trick? Okay, yeah, there's a trick. If I go up, and this is why I really think if you're going to be going on into more math and physics and things, it's really handy to have a calculator with where you can manipulate the stack, where you can go up and grab things. I don't like the 83s don't do that, but the 84s do, and the 89s do, and the Inspires do for the TIs. I really think that's useful to have. So we'll go up, and if I just highlight that and hit enter, it grabs it down to the edit line, so I can just change everything. How do I get all the way over to the left? Second arrow takes me all the way over. Did you know that? Like that, huh? So all I've got to do is just cover up the C in cosine and hit sine. And it changes it. Isn't that cool? Go over to, oops. Cover up the C, hit sine. Cover up the S in sine and hit cosine. And see what I did? Everything else is the same, right? The magnitudes are all the same.
On the 83, if you do the second enter,
It rolls it up. I know it rolls it up. You just got to go a bunch of times to get up there. But yeah, you can do it. You can. So there are my two magnitudes. This one right here is roughly, this isn't exact, but this one is roughly, the x component was 14.1512, blah, right? The y component was about,
Good luck.
good luck, 13, okay, take it to him. 1.66, so 1.670, let's say, I mean, you get the idea, right? But we're not gonna write them down, we're gonna use the calculator. We just wanna now use these two parts to build our right triangle. Because really what we're doing here is we've got the sum of all the x components is r sub x, the sum of all the y components is r sub y, and we're just gonna use that to find what the actual resultant is, okay? So we gotta use Pythagorean theorem. This squared plus this squared equals that squared, right? So on our calculators, we'll just go second square root. I'm just gonna go up and grab that measurement, or that calculation, so I should say, square it, plus that guy squared is that. So there's the magnitude. So I think this is to 3 places, so that would be, what, 19.3 would be the magnitude to 3 places? And I think the units were meters, I can't remember, meters per second or kilometers per hour, meters per second. Now to get the angle, what do we do? So we gotta find theta. So we're gonna have, this is where we take an arctangent, right? Okay, so Elijah, how's that gonna work? Set that up for me. I'm gonna have arctangent of what divided by what here?
The 14 one by 13.
14 divided by,
Other way.
other way. Yeah, we wanna get the y over the x, don't we, right? So we know that theta is gonna equal arctangent of r sub y over r sub x. Does that make sense? Right, because if you look at our resultant right triangle, if this is theta, then the opposite is ry and the adjacent is r sub x, right? Okay, so we can do that on our calculator. We just go second tangent, arctangent of the y component divided by the x component. There it is. Okay. So we're gonna be 42.9 degrees what? How do I describe which direction? 42 north of east, okay, at 19.3 meters per second. That's the velocity of the scooter dude, right around on the boat, okay? Questions? Is that making sense? Okay, good, good. All right, there's one more. This is a really tricky one. This is the last one on the last assignment is really pretty tricky. But let's talk about it just a little bit. This guy, okay? So an airplane, and you gotta really wrap your mind around this one. An airplane flies with an airspeed of 338 kilometers per hour. So what does airspeed mean? That's the speed of the plane relative to the air, right? The air, so that's the airspeed. So if you were, now this would look kind of weird, but if you were in some like kind of a slow propeller plane that had an airspeed, you're flying at an airspeed of 90 miles an hour into a 90-mile-an-hour headwind, what would you look like you're doing? You'd just be hovering there, wouldn't you, right? Does that make sense? So the airspeed is the speed of the plane relative to the air it's flying through. Okay, this plane is flying through a wind current. The wind blows at 39 kilometers per hour at 30 degrees north of east relative to the ground. Now the plane wants to steer due north, right? Well, what's he gonna have to do? If the plane tries to go due north, let's say this represents the plane, how about? So if that represents the airplane trying to go due north, let's say, there's my plane, trying to go due north. Pretty artistic, aren't I? So if the plane steers due north, what's gonna happen to him? He's gonna get blown off course a little bit to the east, isn't he? Right? You see that? Because the wind is it's not blowing totally to the east, but it's got a component that's blowing to the east. The wind is actually blowing to the northeast. But there's a part of that that's gonna push him to the side. Part of it's gonna push him forward, make him speed up. Make sense? Part of it's gonna push him to the side. So what does he have to do then, if he wants to actually steer north? To actually move straight north over the ground? What would you would do in that situation if your plane were being pushed off, you were veering off course? Where would you steer? Steer back to the west a little bit, wouldn't you? Right? He has to compensate. He has to actually point the plane a little bit to the west to compensate for that little bit of eastern wind that's blowing him off course. Right? We got to figure out how much. Okay, so let's look at it this way. Let's say I didn't draw these to scale at all, but if this is oh, I don't want to do that. That's bad. Go back. There we go. This board just confounds me sometimes. Oh, shh. Mr. Lawyer, what are you doing? This is the word. Oh, yeah, look at that. Actually, I like that one. I'll keep that one. Okay, so now if the oops. Oh my gosh, what am I doing? What did I do? Oh, there we go. So this guy here then, let this represent the plane, right? He's going to have to steer at some angle, theta, to the west, west of north, let's say, right? In order to compensate for that. This is if this is the airplane, so let's call it P for plane. Then that's P sub X, and that's P sub Y, right? How does he know how far to steer? That's the crazy part. How does he know how far to steer? Well, let's look at the wind vector. How about? If we look at the wind vector. Oh man, that's not very well. You get the idea. Okay, the wind vector. Wasn't it 30 degrees north of east? I think so. So it's going kind of like this. Now it's a much shorter vector. It's 30 degrees north of east, like that. So that has two components, that component and that component. And this is W for wind. Actually, I won't do that. This is W, vector W for wind. That's W sub X and W sub Y, right? Do you think there's a relationship between any of those components on the plane and the wind? Because ultimately, wouldn't you agree that I'm adding up the velocities of the plane and the wind, right? To find out the velocity of the plane relative to the ground, right? So I'm adding up those two velocities. I'm just going to add up all the components, correct? So what can you tell me then? Does anybody see a connection there? Ponder that for just a second. I'll take a roll here. Anybody see any connections? Does anything have to cancel anything? We got an idea? Could be wrong. What do you think, Ezra?
P of X has to cancel with W.
Ah, yeah. You see that? The west component of the plane has to be canceled. Has to be opposite, right? The same length but opposite direction as the east component of the wind, right? The plane has to have just enough west component, so it's flying just fast enough to the west that it offsets the wind blowing it to the east, right? Does that make sense? Now the north components, we're just going to add up. It's going to make the plane go a little bit faster. But that's what, if we want to go straight, that's the critical part, is we got to get those two components to cancel, right? So let's put some numbers on this instead. How close, well, we might have time, I don't know, we didn't get through it last time, but this class goes faster, we're a smaller group. So remember what the speed was on the wind? I don't remember. 39. So this is 39, and that's 30 degrees, right? And I think maybe it's 39.0 or something crazy like that. No, just 39. 30 degrees north of east. Okay, the plane is 338, right? So this is 338, and the angle, we don't know, it's theta, right? What's the horizontal component of the wind gonna look like then, in terms of the SOHCAHTOA relation, using SOHCAHTOA stuff? What are we gonna get back? What do you think? What's W sub x gonna be? Alyssa, how am I gonna find W sub x? That's gonna, if I know the magnitude's 39.
39 cosine.
Perfect. 39 cosine 30, okay? And what's the x component of the plane gonna be?
Same.
Same, but what would it be in terms of what we know here?
Negative.
True, I mean, it's gonna be negative because it's going that way. But really, all we're really trying to do here is find, let me put it this way. We're trying to find the value of theta in this triangle, right? Does that make sense? And so really, this triangle, we could turn it any which way we want to. We can think of that as being, we can think of this as being positive, it's fine. But we just need to know what the magnitude of that angle is. Let's say that angle ends up being 41 degrees. Let's just say hypothetically. If we want to measure the direction of the plane relative to due east, like say east of north, if that were 41, then what would the whole angle have to be? How would we find it? Yeah, because I'm going to add 90 to it, right? Does that make sense? Isn't it easier, though, to think of this in terms of a reference triangle, we call it in trig? Something that's the smaller triangle instead of this big obtuse triangle, right? You see what I'm getting at? If we can find this angle, this theta, we could really, that's the amount of degrees it's going to be west of north. But we could also say, well, north of east and just go 90 extra degrees, right? Okay? We just want to, we want this magnitude to be equal to that magnitude. What is this one going to be, though? What is p sub x? Magnitude's 338.
338 sine.
Yeah, 338 sine of theta, right? We don't know what theta is yet, but those two have to be equal, don't they? Right? Those components have to be the same magnitude. They're pointing in opposite directions, but the speed has to be the same. So I could set them equal. I could say 338 sine theta equals 39 cosine 30. Okay, now this is kind of strange algebra here, but what are the two steps we're going to have to do to get that theta by itself? What are we going to do first? So I gotta get this, I gotta get that guy by itself. Okay, I got to divide first, don't I? Because the sine is being multiplied by 338, right? This is a tricky one. So if I divide both sides by 338, then look what happens, those cancel. And now I can just take the arc sine or the inverse sine, right? But it looks ugly, but so what? It's gonna be, your calculator's gonna do it, right?
Yeah.
So you end up with theta equals inverse sine of a bunch of junk. 39 cosine 30 divided by 338, right? Does that make sense? Okay. And I just put that in my calculator. Make sense? That's a hard one, though. That's a really hard one. Well, that's, they want two parts of it. They want to know where do you steer. So that is, let's put this in the calculator. That is the answer, in a sense, but we have to interpret it. Where's my calculator? There it is. Okay, so we get arc sine, and I always say arc sine and inverse sine mean the same thing. Same, different words for the same thing. So arc sine or inverse sine of that ratio. So I'm gonna be fancy here, but keep it organized. Use a little fraction template. And then we get 39 cosine 30 divided by 338. Let's go over and close the whole thing. And we get 5.7 to 2 places, right? So he's only, he'd have to steer very far to the west, only 5.7 degrees to the west, because he's going so fast, right? That's him steering a little bit still gives him quite a bit of horizontal speed, because he's going so darn fast.
That's the answer?
Well, but I'm not sure. Let's look back up at the top, because I think the answer actually wanted it to be how many degrees north of east. Now look at our picture. That's not what we measured, is it? We measured how many degrees west of north, so we have to add an additional, the theta's got to go has to go all the way from there to there. So I got to add 90 to it. Right? See what I'm saying? Okay, good. That's a lot of physics today we did. That's good stuff.